All right, so we finished about talking about splitting, but let's continue and then put everything together into this reference model. So this is typically how the OSI model is depicted. We have the physical representation of this is that we have some application software running on a host that's using the network, which includes then routers and whatnot, routers, links, and so forth. And then there is another host at the other end of the connection with some application program. So this is called one end system, and this is the other end system. And at this host here, we have all layers, the 7 layers. And if you remember, typically the first 3 layers here sometimes is merged into the application layer. So we have layer 1, 2, 3, 4, and then application layer number 7, like this. So at the end nodes, we have all the protocol layers. But in the routers, we don't have any application software running, and therefore there is no need for the application layer. And it turns out that how things are done in the OSI layer, we don't need a transport layer in the routers. Okay. So the routers have a physical layer, data link layer, and the network layer. The difference, the protocols which exist only at the end nodes are called end-to-end protocols, because they work from the entity at one end is talking to the entity at the other end. Okay, so these are called end-to-end protocols. These are not end-to-end protocols, and the difference is that the process here, the network protocol process here, is talking to another network process inside the network in the router, which is talking to this router, which is talking to this one. So communication is actually going end to end here, but it goes through these intermediate network layers. So we'll see how that works in a few minutes, actually. Okay, but end-to-end protocol on the top, and then these are not end-to-end protocols. Questions? Okay, and we can have as many layers, as many routers as we like here in between, of course. So I'm going to skip this lecture quiz and then just wrap up a few things about each layer here. And some of this might not be so easy to understand right now, so I'll just put them down a little bit as a reference. But please read more about this in the book. So the physical layer, which is in the bottom, the service it provides is transfer of frames which it gets from the layer above it, and frames are block of bits. Okay, so and across a physical channel, so wires, fibers, etc. So the specification of physical also is responsible for the physical aspects of the communication link. I mean, mechanical stuff, how the cables are specified, and what performance they have, how this connection should look like, and so forth. Electrical, optical properties, what modulation, what signal strength, voltage levels, and so forth. And a little bit on functional things, for instance, how to activate, maintain, and deactivate the physical link. So basically, it takes the bits it gets from above, which comes in a block, and then converts them into bits, and then transmit this over a channel. I'll talk more about the physical layer tomorrow. Data link layer, which is above the physical layer, provides a service, and it provides a service of transfer of block of bits called packets. It gets packets from above over a link that connects 2 nodes directly or via these switches. We will see more about that later on. And it implements a number of things, maybe not all of these, but these are things it could implement. Framing, which is a way to put in markers in a bit stream, so we can figure out when a block starts and another block ends. Flow control, and this is to regulate transmission speed in order to avoid overwhelming a slow receiver. So if I'm a fast transmitter, if I can transmit a gigabit per second, but I know my receiver can only receive a megabit per second, there is no need, I cannot transmit a gigabit to that. I mean, it will kill that, it will simply not work, right? So I have to adopt my transmission speed in order to accommodate the receiver's capabilities. Error control, medium access, we'll talk more about this, multiplexing, addressing, activation maintenance, and deactivation of these link connections. It goes a little bit fast here, but we will talk more about this later on. Network layer, transfer service is transfer of segments it gets from the transport layer, implements these things, not all of them, depends on the service. Fragmentation, reassembly of segments, transfer of packets over multiple links and networks. Routing is to find a path through the network. Forwarding packets over a node. And addressing schemes, flow control, multiplexing of several protocols above us. Congestion control. And congestion control is like to avoid that the network is flooded with bits, which would then become overflows in buffers, and we would lose a lot of packets as we go across the network. The network will basically crash. So congestion control is an important thing here. And then connection setup, maintenance, and release, and then internetworking that we will talk about in a few minutes. Transport layer, end-to-end transfer of application layer messages. Many different types we can do this. We'll talk more about that later on. And then a few things it can implement. Go a little bit fast here. And then layer 5, 6, and 7, basically layer 7. Session control is to control in which manner data is transmitted. I mean, if it's half duplex or full duplex or whatnot. And presentation layer takes care of translating between different formats. For instance, character codes could be encoded in different ways. And provides then useful services for the layer above it. Okay, so I think that finishes off this first lecture, and so then now let's get into lecture number 3. So welcome to lecture number 3. So about internet working and TCP/IP architecture. So remember, in the previous hour we talked about the OSI model, which I said is the theoretical clean model for how to split up functionalities between different layers. It uses 7 layers, or actually only 4 layers typically, and they are well specified what they should do, and so forth. We have this idea about protocol data units, service data units, service access points, and all these things. Clean, nice theoretical model. Now, it's not used in practice. What is used in practice is the TCP/IP architecture, which is more messy. It breaks a few of the rules that the OSI model actually puts up. But since it's used in practice, it's also important to talk about that. Okay, so terminology, we have networks, we have nodes, and nodes could be hosts or routers. Hosts are at the end of the network, routers are inside. We have links interconnecting these nodes. We have applications, which is user software running on top of end nodes that provide services to users, typically humans. We have layers, and layers is a set of communication functions that provide a service up by using the services below. We talked about this. Service could be connection-oriented, connection-less. Protocol, a layer can contain many protocols. So it's fairly important that a layer, many protocols. but not the opposite. So a protocol doesn't span several layers. We have these entities which are software running in a layer that executes a protocol. Peer processes are communicating by exchanging these protocol data units, and layers at the same node communicate by exchanging service data units as they go down the stack and control information over a service access point. Service data units are encapsulated into PDUs, protocol data units. So a PDU is an SDU plus header and trailer. Not always a trailer, but sometimes. Okay. Layers can fragment and so forth. We just talked about this, so let's move on. And then talk about the OSI model. Looks like this. We already talked about that. Okay, so now let's go into new things. The Internet Reference Model. Okay, so we have the OSI model here. 7 layers, or actually just 5 layers. And then we have the original Internet model, and the Internet model as defined in the book. And if you Google something, I'm sure you can find a third or a fourth variation of this. But we will actually try to stick with the model as it's described in the book in order to avoid confusion. The original model looks something like this. It had the application layer, it had a transport layer, an internet layer, and a network interface layer. There is not a nice clean mapping between these different layers here. I mean, the internet transport layer is basically the transport layer in the OSI. The internet layer in this model has some of the functionality of the network layer in the OSI, but not all of it. And the network interface layer here contains functionality from layer 1 and 2 from the OSI model and parts of 3. Okay. So it's a little bit messy here. You cannot really translate the layers one by one like this. The internet model as used in the book have 5 layers also: application, transport, network, data link, and physical. So you see it's not actually a good one-to-one mapping towards what's in the internet original internet model. For instance, here is 1, 2, 3, 4 layers, and here is 5. But we'll stick with this one. When you Google, you can find this. Okay. And the internet model is also called the TCP/IP model. So it's the same thing. So now, when we talk about protocols, now we talk about practical things here, the protocols that are used in practice. The question is, who decides on this? And there are various different standardization bodies that do this, and they have different domains of where they specify protocols. And some of these perhaps you have heard about and some perhaps not. But there is something called the ITU, the International Telecommunications Union, I believe. The area is in telecommunications, and they specify some things. And maybe you recognize MPEG-4 here as one of these standards. So that's an ITU standard. IEEE, that's how to pronounce this, deal with communications, Ethernet, Wi-Fi, other things. And then we have the Internet Engineering Task Force, and they're responsible for some of the protocols on the internet, for instance, HTTP or DNS and so forth. And then we have the World Wide Web Consortium something. I'm not sure exactly what it means, but they're responsible for web standards, for instance, HTML, how to specify that language, CSS and other things. And then we have something called 3GPP, which specify mobile wireless standards, cell phone standards. So GSM, 3G, LTE, LTE, which is 4G, and now, LTE is 4G, but then also now 5G. It doesn't have any other name than 5G. And there will be like 6G, keep on going like this. Okay. So basically how it works is that people get together and they talk about their problems and they figure out a good way to solve this. They publish a standard saying these are the rules, and then manufacturers reads these documents and then implement stuff according to these standards. And if they've done a good job both in the standardization of the protocol and the implementation of the protocol, a switch from Netgear would work beautifully with a switch from Cisco. Right? So interoperability is a very important thing here. And this is crucial to create a mass market and economy of scale and so forth. So let's now talk about internet working. And this is the key thing to get internet to work. Okay? So the internet as we know it is a interconnection of many different networks. So here we have a complicated example where we have Alice. Alice is sitting at her laptop and would like to communicate with Bob down here. And Bob is sitting by his computer here, or maybe Bob is a server, I don't know. So Alice has a need to communicate with Bob. Bob is attached to a local area network here, which is attached to a internet service provider over a wide area network into another wide area network with another service provider, and a third service provider over here with another wide area network, and then it goes into the local area network where Alice's computer is attached to. So how does information go from Alice to Bob and vice versa? How do we get this to work? Well, there are these protocol stacks. So we have a full stack at the end nodes, and then in the middle we have reduced stacks, 3-layer stacks in this case. So logically, information goes like this. It goes from Alice to the routers, through the routers, up and down through the network, up and down in the network stacks until it reaches Bob. So information goes down the stack over a physical link to the router number 2, goes up to the network layer in router 2 and down to the physical layer here, which connects router 2 and 4 to each other and so forth. And it goes like this. So that's how it, logically works. Another way to look at this in an even more simplified way is that we have Alice on the top and Bob at the bottom, and information goes over these clouds, which are networks, interconnected with routers. So we can think of routers as being between two networks. So we have host, network, router, network, router, network, router, and so forth. So that's a even cleaner picture of what's going on. So that's what we would like to achieve. Now let's go into more detail and see how is this actually done? How do we go from here to here and so forth? How do we do this with practical protocols? Okay. Actually, before we do that, let's talk a little bit about the TCP/IP protocols. We already give a few examples about this. So we have on the top application layer, transport layer, network layer, and then we have at the bottom data link and physical layers. So on the top we have this HTTP, SMTP, DNS, DC, DHCP, and so forth. Many protocols. These use then protocols, the application layer protocols use the layers, the protocols at the transport layer. And that's a typo here, but we have TCP and UDP, and then we have STCP, not SCP. So this is, okay, so there's a typo, it should be STCP, okay. So these are different types of transport protocols. And then we have the famous IP protocol in the network layer and some other protocols which are basically helper protocols to IP. And below IP we have data link and physical layer protocols. And here we can ADSL, LTE, Wi-Fi, fibers, Ethernet, whatnot. There are many things that goes on here. And the beautiful thing here is that IP hides the complexity of and the special properties of all of these, and it gives a uniform interface to these transport layers. So the transport layers here don't need to worry about whether its data goes over LTE, Wi-Fi, ADSL or Ethernet. It can work in the same way, regardless. So that's the beauty of it. All right. So what type of services is provided by IP? IP provides best effort, connectionless packet transfer. So what does this mean? Best effort means that basically if I'm IP, the layer above it, I say, hey, I can transmit bits to you or packets, but I won't guarantee anything. Right? I'll try my best, but no guarantees. Okay, so I get a packet from above, I send it over, maybe it arrives, maybe it doesn't. Okay, that's best effort. Connectionless means that when I get a packet from the layer above, I simply transmit that without checking whether this IP address is a valid address and whether the computer on the other side with this IP address is even turned on. Okay, I just transmit. I don't try to establish a connection with the receiver before transmitting the payload. I just take the payload, wrap it into an IP packet and send it on its merry way. And hopefully it will arrive. No guarantees. So that's what IP does. Sometimes this is good enough and sometimes it's not good enough. So therefore, the transport layers that we have above, there are a number of important transport layer protocols. We won't talk about all of them, but UDP is one which is heavily used. And UDP basically does nothing in order to refine the IP service. It is basically just a wrapper around IP. So it provides best effort, no guarantees, connectionless, and it says datagram service, which is essentially the same as transmitting packets. Just transmit packets. That's what you do. And sometimes this is good enough for the application layer protocol and sometimes not. If it's not good enough, then one can use a better service or, let's see, a service with more other features. Whether it's better or worse is actually not so clear, but something which is more refined. So TCP provides a reliable service. It's connection oriented, it's full duplex, it's byte-based stream service. Okay, so that's a mouthful. So first of all, if I'm TCP, the layer above me will hand me bytes, individual bytes. We'll just fold down bytes here. And what I say to the service above me is that I will make sure that every single byte you give to me will arrive at the receiver in the right order, error-free and in right order. So that's the reliability. That it's connection-oriented, it's not so important for the protocol above it, it's just how I implement the service. And TCP, what it does is that when I get a request from above to open up a connection, I establish a connection first. I check that there is actually a receiver out there and that that receiver is willing to talk to me. So that's the connection-oriented there. Full duplex means that data flows both up and down, unsynchronized with each other. Right? So I can have full duplex, information going at the same time in both directions. Byte-based, I said, okay, so I can transmit individual bytes from a stream of bytes, and there is no end to this number of bytes. I can do this indefinitely, as long as the service above me would like to transmit bytes. Okay, any questions? Okay, And then if this is not good enough, there are other transport protocols. And one, I just wanted to mention one. Okay, so UDP and TCP are used heavily, right? A lot. But in some cases, there are special services where you, special requirements that you would like to have something even better than TCP. And then there is this let's see, stream control transmission protocol or something like that. Okay. Anyways, what it does is it does the same as TCP, but it adds multi-homing message-based multi-stream service. So multi-homing basically means that we can use several IP layers at the same time. So that is basically we have parallel IP paths through the network, and this is good for reliability. Message-based means that instead of accepting byte by byte, I can accept a larger block of bytes. And multi-stream basically means that I can have two streams going at the same time from above. Okay, so I will guarantee that the messages I get from above will be delivered to the receiver in order. Okay, and it will be in order for each of the streams I get from above. Okay, and that's sometimes useful. Questions on this? Okay. So let's talk about this. We already talked about internet names and internet addresses, but let's refresh our minds what these are. So internet names are unique and easy to remember, independent of physical location, and is split into two, has two parts, host and domain name. Okay, so www.chalmers.sc is consisting of two things, a host and a domain. Okay. An internet address is an IP address. It's the same as an internet address. Address uniquely and something called an interface network interface card. We'll explain that more in a second. So this NIC or network interface card can have several IP addresses actually. A node can have several IP addresses, for instance, when it's attached to several networks. But anyways, the routing decisions are based on the destination IP address, as we will see in an example soon. And IP addresses have two parts, a net ID and a host ID. So a version 4 IP address is usually written like this, 129.16.17.21. We have 4 groups here of let's see now. It's 8 bits per group, so it's 32 bits in total. And these are then numbers that goes from 0 to 255. Okay, so 0 to 255 here, 0 to 255 here. So, and these are split into a net ID and a host ID, and where the border goes is flexible. So it's not like here we have a clear border between the host and the domain. It goes here. Where this border goes here is unclear. It's flexible. But anyways, it's split into 2 parts, which is the important thing. Okay. Link layer addresses are local area networks, and other networks have these link layer addresses, which are then assigned to physical attachments to the network, which are these network interface cards. And they provide then addressing for that local area network, but only for that local area network. So to illustrate how this looks like, we can say that suppose we have a node here. Okay, so it could be a host or a router, some node. Suppose it's a host, actually a web server. then it can have a internet name, maybe this one, right? So this is the internet internet name. Okay, so this is some type of machine, right? And attached to this machine there might be a network interface card. Okay, there might be several network interface cards. Okay, depending on the type. A server typically have more than one. Okay, this network interface card, if we have an IP address, say IP1, an IP address, that points to a network interface card. Okay, so there, an IP identifies a network interface card. However, a network interface card might have several IP addresses. Okay, so you cannot say that this network interface card has a certain IP. It could have several. That's possible. Okay, and then we can have here also, you know, IP4, so 3, and for instance, maybe this one only has one IP address. Okay. These are called network addresses. And to translate between the internet name and the network address, we use the protocol. You remember which one? TCP, UDP, Ethernet, HTTP, DNS, domain name system. Okay, translates between these two addresses, right? So if I have this internet name, it will then give me network address, or network addresses actually. Okay. One internet name can have multiple IP addresses, and actually vice versa. Okay, so an IP address is associated with one or several internet names, and internet name can have several IP addresses. Okay. Now, on top of having this box having an internet name, a bunch of IP addresses, each interface card also have one single physical address. Okay, and these are called link layer address. And for example, I mean, if an example of a network address is IP address, an example of a network layer address could be an Ethernet address. Link layer addresses is also known as, aka, as physical address or MAC address. Okay. And MAC stands for medium access control, but it's not important at this point. So we have internet names, we have network addresses, we have link layer addresses. Example of link layer address could also be known as a physical address or a MAC layer address. And an example of this is an Ethernet address. Okay. Now, there is only one hardware address, MAC address or link layer address per network interface card, but you can have several IPs. Okay. Now, important is that this is fixed in time. So, meaning that when the network interface card is manufactured, it gets a serial number essentially, and this is the physical address of that, and it remains like that forever. At least in theory. In practice, they could be reprogrammed, but for simplicity, let's say that these are fixed now. IP addresses are dynamic, i.e. can change in time. So actually, you get an IP address when you power up. So my laptop here has a certain IP address right now. When I move over to my office and power this up again, it will probably get a new IP address, and for sure it will get a new IP address when I go at home. Nevertheless, the interface cards here retain their physical addresses. They're there forever. Question on this? Okay. All right. So going back here to the slides, one needs to translate these. There is a need for translation between different addresses from network address to link layer address. There is a need to translate with this. And that is done with this protocol called ARP. Stands for Address Resolution Protocol. So for example, Ethernet has 48-bit addresses. Okay. Each Ethernet network interface card has a globally unique address, MAC address or physical address or link layer address. It's 24 bits. That the first 24 bits identify who's done it, who's the manufacturer, and the last 28 bits is a serial number. So for instance, if this is typically how this is written. So here we have a hex number or two hex numbers, hexadecimal numbers. So okay, so it's from 0 up to F. Okay, F being 15. Okay, so these hex numbers, the 12 of them, there are 6 bytes, 48 bits. And the first 24 bits here identify the manufacturer. So this one, if one gets an address like this, one can look at the first 24 bits and figure out who's done it. Okay, in this case, Apple. Right, and then here is a serial number. So we can think of the physical address almost, in a human context, this would be your personal number. Something you get when you're manufactured or actually delivered, right? Then you get your personal number. And that sticks with you forever. While the network address, you can think of that, that's where you live, right? You move to different places, you have different addresses. Okay, link layer addresses. There are 3 main types of these. So I said that they uniquely identify a network interface card. And that's true, but sometimes there is also the need to address many network interface cards which are attached to a network. So we need also other types of addresses, namely those who are called multicast and broadcast. So unicast link layer addresses is this serial number that I talked about earlier, right? So that identifies one network card on this planet. But then there are multicast, which addresses more than one of the nodes on the local network. And then we have broadcast, which addresses all nodes. And we will see we will actually need these broadcast mode to get things done. right? We sometimes need to talk to all the nodes which are attached to a network. So the Ethernet addressing scheme here is such that the second hex digit here, if that's even, then we have unicast. And unicast basically means that it identifies one single network interface card. A broadcast can identify all network interface cards, and a multicast more than one. So a unicast address looks like this. It's not important that it looks like this, but it's just for your information, right? And it's information because there is a typo in the book. They mixed this up. Anyways, and multicast, then the second one is odd. The broadcast address is all Fs. Okay, so it's the 111111111 address. Okay, and that is picked up by every node who can hear that message. Okay. So how to obtain and resolve, that is translate between these addresses. We know that we have, how do we get an internet name? How did Chalmers get this? Well, basically Chalmers bought it or rents it. So you go to a special company called the domain name register and you say, hey, I would like to have this name. And if that name is available and fulfills some basic requirements, then you get it and you pay for it. And you pay different amounts of money depending on what type of top domain it is, if it's a .sc or .tv or .com or whatnot. So you can buy this. So Chalmers has done this. And once this is done, then the network register keeps track of this and so forth. Okay. The IP address, on the other hand, okay, so the internet name is dynamic. It can move around. It could be at different computers all the time. So an IP address is typically dynamically assigned at power up through this protocol called Dynamic Host Configuration Protocol. You can also have fixed IP. So a computer at every power up, it gets the same IP address. This is a little bit tricky because it's a configuration and sometimes there are mistakes done and so forth, but you can do that. Okay. Most often for consumer things, you get it through this DHCP. The link layer address is assigned by the manufacturer at when it's the network interface card is manufactured. So both the internet name and IP address are dynamic. They can change in time. The link layer address is fixed. It remains the same for all eternity, at least in theory. We know we can reprogram them, but let's think of them as being fixed. When you want to translate between an internet name and an IP, we use DNS. And to translate between an IP address and a link layer, we use ARP. Okay. So, small quiz to see whether we are on the same page. Which of the following is a network address? An IP address, a MAC address, or a port number, or this www.chalmers.sc. So, maybe I should do this. 1, 2, 3, 4. How many for 1? 2, 3, 4. It's correct one is 1. So IP is a network address. Link layer address, is it? Then we know it's not an IP, right? But is it a MAC, port, or www.chalmers.sc? 1, 2, great, 3, 4, no. Okay, good. So this seems to be quite clear. Now I'm getting a little bit soft in my head. I see that you're also a little soft. So let's take 15 minutes. I need a cup of coffee. I don't know about you guys, but yeah.